Video for section 1.7 for pre-calculus, and we are looking at word problems. So the first part of this is just going to be straight out of your book. I'm just going to go through some of the examples that they have. So if you want to follow along, we're on page 152. So I'm starting with example 2. We have something called a maximum value problem. All of this section is just word problem applications that kind of ties into section 1.1 that we started, where we were looking at functions and graphs and numbers and how do those apply to real life situations. Now that we know what functions and what properties functions have, we can now apply them a little bit more to these types of word problems. Okay, so we have this situation with a piece of cardboard. So we're looking at this thing right here. It says a square of side X is cut. So we have these squares, and there's one cut out of each corner of an 8-inch by 15-inch piece of cardboard. Okay, so this right here is X, and this right here is X. All of these are X. Okay, so the first thing we need to do is write the volume V of the box as a function of X. So the volume of a box or a rectangular prism is length times width times height. And so we're using that. We have to determine what the length and the width and the height are in terms of the X. Well, if you cut these out and fold it up, that means that this right here is going to be X. And I wonder if there's a way I can zoom in. There is. Okay, that would work a little better. So this right here is going to be X. And we need to figure out this and this. Now, whichever one you call the length and which one you call the width, it doesn't matter. I'll call this the length, call this the width. All right, so this would be the length. And remember, they told us that the whole thing is 8 by 15 before we cut out the X squares. So to figure out from here to here, we need to do 8 minus 2 x's, right? Because we're cutting off an x here and an x here. So that could be our length, 8 minus 2x. And then our width is similar. The whole thing is 15. Again, we're cutting off 2 x's. So from here to here, it's going to be 15 minus 2 x's. So that would be our width. So if we multiply x, 8 minus 2x, and 15 minus 2x all together, we get the volume in terms of x. So that's the first thing that we have here. The box will have a base with sides 8 minus 2x and a length of, okay, base, whatever, it doesn't matter. Okay, so there's our formula. The second question says find the domain of the v as a function of x. Okay, now the domain of this thing, which is really just a cubic function, this thing right here, would be all real numbers. But remember, there's something called an implicit domain and an implied domain. Or sorry, relative domain and an implied domain. Yeah. That's what it's called. Okay, so I mean, the real domain of this situation is dependent on this box. X can't be anything. We can't cut out any size. Obviously, we can't cut out a negative length for X. And the other thing is we can't cut out anything more than 4, what is this, inches? Yeah, inches, okay? Because if we cut out, if X is 4 inches and this whole thing is 8, right? Then you're going to have nothing left here, right? You cut out the whole side. Now, if you actually let x equal 4 in the problem, here's what's going to happen. Get 4 times 8 minus 2 times 4 would be 8. 15 minus 8. You get a 0 right here. which tells us that the volume would be 0. And that actually makes sense. I mean, it's kind of weird to have a volume of a box that's nothing, but it makes sense for the problem. So I'm going to, that's why they say it is inclusive with the 4. Okay, so it's inclusive at 0 and inclusive at 4. And they explain that right there. They say the endpoints give a box of no volume, which is mathematically feasible as other 0 concepts. Okay, so mathematically it works just fine. And it makes sense for the picture too. I mean, you would have a box with no volume because you couldn't fold up the box anymore. But anything less than 0 would be a problem. Anything more than 4, if it was like, if this was like 5 inches here and 5 inches here, then that doesn't make any sense because this is supposed to be 8. And so that makes absolutely no sense. Okay. All right, so if you graph this thing, and they did, you can graph this in Desmos. It's not going to look like this. It's going to look a little different because this is scaled out a lot. This is from 0 to 100. So this is going by like tens. This is 1, 2, 3, 4. Okay. And 0. So this is just scaled along our domain very drastically. Okay, so what this represents, this axis, this is the volume axis. Okay, so we're looking at this question now. Graph V is a function of x over the domain found in part B that we found. And use the maximum finder on your grapher to determine the maximum volume such a box can hold. Now, we're looking for the maximum volume. So you're looking for a relative max. And if you are using a graphing calculator, there's a tool that allows you to just find that. Or in Desmos, you'll just see a little dot here, and you click on it, it'll tell you what it is. Okay, so if we click on it, you can see that the point is x equals 1.666666 repeating and y equals 90.74. So that is the largest volume that you can create with x being this number of inches. Any less than that, then the volume is less all the way down to nothing. Any more than that, the volume is less all the way down to nothing on the other end. Okay? So this is something that a person would want to know, or a company would want to know, if you were creating something that was a package or something like that. You want to know what the volume would be with the least amount of material, right? We're kind of using the same piece of cardboard and creating different volumes with it. The next thing we're going to look at is example 3, the antenna problem. So it says a small satellite dish is packaged with a cardboard cylinder for protection. The parabolic dish is 24 inches in diameter and 6 inches deep, and the diameter of the cardboard cylinder is 12 inches. How tall must the cylinder be to fit in the middle of the dish and be flush with the top? Okay, now this picture is not really showing it really well. The cylinder, the circle part of this cardboard cylinder is right here. If I could draw it, okay? Alright, so we're going to use a graph to create this. This is a parabolic dish, so that means that this is a parabola. And a parabola, we can graph. We know a lot of things about the graph of a parabola. Okay, so what they did was they transferred this shape of this parabola onto a graph, and they made the vertex 0, 0. Okay, so since this diameter here is 12, that means that we're going to go, or sorry, 24. The diameter is 24, so this is 12 on either side. And then the 6 is, they tell us that this is 6. So from here downward it's 6. So that's how they got these 2 points here. We've got the 12, 6 and the negative 12, 6 on either side. Okay, so those 2 points we can plot. So why do we need that? We need that so that we can create an equation for this parabola. Since the vertex is at 0, 0, there was no horizontal or vertical translation whatsoever. So it's just y equals k times x squared, because we did have a shrink, a vertical shrink. So we need to figure out what factor it was shrinking by. So we have these 2 points, 12, 6 and negative 12, 6. We can plug them in, and we can solve for that k value that it was shrinking by. And it turns out it's 1/24. So the equation of this parabola, as we have created it in the graph, is y equals 1/24 x squared. So from there, if let me clear some of this stuff out. If we place in the cardboard insert, okay, so here's the top, if I can draw straight. And the cardboard insert had a diameter of, they told us, 12 inches. Okay, so from here to here, it's 12. So it's right in the middle, so we're going 6 left and 6 to the right of this. So if we go 6 on either side in the graph, there it is. And I can just drop it down till it hits the parabola. Now, I'm not sure exactly where this is. It looks kind of like 2, but I'm not sure. So how we can figure out where that is here and here on the parabola, which we know the x value is 6 something and negative 6 something. So what we can do is we can plug in 6 into the equation that we found. So let x equals 6, and it turns out that y is 1.5. So the question was, how tall was the cylinder? So now we know that this is 1.5. We can figure out what this is, because this is from 1.5 to 6. That gives us 4.5. So this is 4.5 inches. Okay? All right, now this right here that you see, you're going to need to print out. It's called 1-7 Key Concepts or something in the Pre-Calculus Documents folder, which I think you guys know where to find that now. Get 3 word problems. You need to pause the video, go find this. Okay, first problem. A tabletop is rectangular. Its length is 2 feet less than twice its width. The perimeter is 16 feet. What are the dimensions of the tabletop? Okay. That's a terrible rectangle, but all right. So we have a length and a width. They tell us that the length is 2 feet less than twice its width. Okay. So the width I'm just going to call W. So the length would be 2 times W and then 2 feet less than that. Okay, the perimeter of a rectangle, remember, is you got 2 W's and 2 L's. So 2W plus 2L. So then I'm just going to substitute 2W minus 2 in for L. So 2W plus 2 times 2W minus 2 equals the perimeter, which they tell us is 16 feet. Okay, so it's a simple equation from there. 2W plus 4W minus 4, 6W minus 4. Add the 4, that's 20 divided by 6. So that's W, we can reduce it to 10/3. Okay, then we can plug it in. That's right here, so that's W. So L equals 20 thirds minus 2, which is 6 thirds. So that's 14 thirds. So our dimensions are 14 thirds feet by 10 thirds feet. All right, number 2, XYZ company has fixed annual overhead costs of $150,000. So annual overhead are like things like rent, things that you have to pay in your company that you have really no control over. So those are costs that you spend. Each employee generates $68,000. The company pays $40,000 for each of the employees' salary, benefits, etc. How many employees are needed to earn a profit of $214,000? Okay, so you need to think of this in positives and negatives. Okay, this is a negative. This is a positive, and it depends on how many employees you have, though. This also depends on how many employees you have, but it's a negative. And this is what our goal is. So think of it as, okay, we have negative 150,000 right off the bat. And if we let X equal the number of employees, then you're going to have to, you're going to earn 68,000 times X for the revenue for each employee. But then you have to pay them $40,000 times X. And that we're looking to see, when is this going to be a profit of $214,000. All right, so the hardest part here is just coming up with this equation. Now, this is cumbersome to deal with all of these zeros. So if you divide everything by 1,000, you're going to end up with something more like this, which is much easier to deal with. So I'm just dividing everything by 1,000. So through all three zeros at the end are just going to go away. All right, so then that's 28x. Negative 150 plus 28x equals 214. Add the 150, add the 150. 28x is equal to 364. Divide. So it's 13 employees. All right, number 3, the mixture solution ones. Now you probably have seen these before. This is like an algebra problem. The basic idea is you have a beaker and you're with some stuff in it, and you're mixing some more stuff in it, and you get a mixture. Okay. So our first situation is we have 400 milliliters of a 15% solution. And then we're going to mix that with an unknown amount of milliliters of a 40% solution, and we want to get a 35% solution. So if you multiply 400 milliliters times the 15%, you get 60 milliliters of just the benzene. That is what's in here. And that's what I got that by multiplying 400 times 15%. So 0.15. Okay. Now, if we have X amount of 40% solution, then 0.4 times X will be how much benzene is in there. Okay. Now, they didn't tell us how much of the 35% solution we have, but actually we do know. We know that this is going to be 400 plus X milliliters, and that's because we're mixing these two together. So just adding them together. So the amount of benzene that we're going to have is 0.35 times that amount. So the amount of benzene in here plus the amount of benzene in here has to be the amount of benzene in the total. So we get this equation. 60 plus 0.4x equals 0.35 times 400 plus x. I'll leave that to you to solve it. All right, that's it. So this page that you printed out, just keep that. We'll put that in our notebooks next week.